Geodesy is the study of shape of the earth and its gravity field. Crustal deformation studies focus on changes in shape of the earth's surface and geode, thus emphasizing active processes of strain, mass transfer and loading, geodynamics, plate tectonics, earthquakes and fault slip, magmatism and volcanism, and global change studies all trace some of their most important advances to mundane or even arcane geodetic observations. Hence, anyone studying active earth and planetary processes will benefit from the understanding of both geodetic measurement and the geodetic signatures of these many different processes. Geodesy is a highly quantitative observational metric. Crustal deformation guides us to examine several of the physical processes that can be studied with geodesy. Emphasis here will be on solid earth processes, that is, various processes and timescales of fault slip, magma flux or intrusion processes, viscoelastic rebound and flexural isostasy, etc. Deformation of the rock takes place due to the factors like forces and stress, the geothermal gradient, folding and faulting, and how horizontally directed plate motions cause vertical uplift. Now, let us discuss these aspects one by one. Forces and stress. Rocks change their shape and volume when they are subjected to stress. Stresses are caused by forces that are exerted on the edges or interior of a material. A wide variety of physical processes exert stresses on rocks. For example, gravity constantly exerts downward stress on all rocks. Temperature changes cause thermal expansion and contraction that can cause rocks to fracture. Wetting and drying similarly can induce or enhance rock fractures. On a large scale, horizontal plate movement exerts lateral, that is horizontal and vertical stresses on rocks. And of course, the accumulation of thick layers of sediment can exert immense downward pressure on rocks that are buried underneath. The next aspect is the geothermal gradient. The strong dependence of rock deformation on temperature is hardly surprising. For example, wax will fracture if it is chilled and then subjected to a sudden stress, such as dropping it on a hard floor. The same wax will bend if heated to moderate temperatures and will flow like water if heated to high enough temperatures. Anyone who has been in a deep mine has experienced the phenomenon of increasing temperatures with depth beneath the earth's surface. The geothermal gradient ranges from roughly 10 degrees centigrade per kilometer of depth in stable old continental interiors to 30 degrees centigrade per kilometer of depth along active plate boundaries. 10 degrees centigrade per kilometer equals roughly 29 degrees Fahrenheit per mile. So, for example, if the surface temperature of rocks is about 60 degrees, then the rock temperature at a depth of 1 mile is about 89 degrees in a continental interior. The geothermal gradient is important for several reasons. On a practical level, some gold mines reach depths of 3.9 kilometers and have geothermal gradients that average 30 degrees centigrade per kilometer. The implied temperature at the deepest levels of the mine is 3.9 kilometers multiplied by 30 degree centigrade per kilometer is equal to 117 degrees centigrade plus 20 degrees centigrade the surface temperature. The overall it is equal to 137 degrees centigrade. The next one is the folding and faulting. Rocks undergo deformation due to tectonic activity, and the most spectacular form of ductile deformation is the rock folding. Folding is a ductile behavior in which planar layers of rock bend in response to stress. Depending on whether the hinge of a fold, that is the point of sharpest curvature, points up, down or to the side, a fold is respectively called an anticline, a syncline or a recumbent fold. Faulting is a brittle behavior in which a rock responds to stress by developing one or more fractures. Deformation of the rock concentrates along the fractures. Slip along faults frequently occurs through sudden ruptures resulting in earthquakes. Before seeing some examples of faults, let us first review some simple terminology. A footwall is the underlying surface of a fault plane. A hanging wall is the overlying surface of a fault plane. The footwall thus consists of rocks that lie beneath a fault surface. One could stand on the footwall of a fault if the hanging wall rocks were removed. Similarly, if one could somehow remove the footwall rocks, one would have to hang from the hanging wall rocks. Faults can be grouped into several categories depending on their geometry and the type of motion that occurs across them. The following are the three types of faults. Reverse faults: hanging wall rocks slide upward along the fault surface and thus thrust over the footwall rocks. A thrust fault is a reverse fault that is inclined at angles of less than 45 degrees from horizontal. Normal faults: hanging wall rocks slide downward along the fault surface, giving the appearance that the fault wall rocks are sliding upward. Strike slip faults: lithosphere on either side of the fault moves horizontally in a direction parallel to the fault. Next is the mountain building activity. As plates move around the earth's surface, they exert powerful lateral forces on rocks. The response of the crust to those forces give rise to deformation on a large scale, particularly along plate boundaries. For example, dozens or hundreds of large scale faults can form in zones of plate convergence, resulting in a broad and high mountain belt. Here is a list of geologic processes that can result in mountain building, that is crustal shortening or thickening in response to the convergence of a subducting plate, continental collision, uplift of sediments accreted by subduction, volcanism, corner accretion or uplift due to along trench rafting of terrain, heating or cooling of lithosphere by the underlying mantle and hence uplift or subsidence, and crustal extension. Developing an understanding of each of these mechanisms for uplift will require much of the remainder of the course. For the remainder of this lecture, let us review mountain uplift as a consequence of horizontal plate displacements. Geometrically, if two plates are colliding, they can respond as follows. One plate can subduct into the mantle. One or both plates can undergo shortening and hence uplift and crustal thickening. One or both plates can undergo lateral extrusion, that is, part of the plate escapes the collision zone by extruding sideways. Factors that complicate calculations of total uplift. The simple geometric exercise above is designed to give you a feeling for the magnitudes of vertical uplift that might accompany horizontal motion. Plate convergence of hundreds or even 1,000 kilometers or more over millions of years might be accompanied by only several kilometers of uplift. This uplift, while spectacular to the eye, is merely a small part of the displacement budget, which is largely dominated by horizontal motion. The geometric exercise ignores many important aspects of mountain building and cannot be used as a technique for predicting total topography given total horizontal motion. Why is this the case? Fault dips are rarely well known and faults are often curved, with their dips increasing towards the surface. Erosion or mass wasting removes material from the upper reaches of uplifting regions, sometimes nearly as quickly as the region is going up. Vertical uplift must fight the downward pull of gravity in extreme cases. No amount of horizontal convergence is capable of causing further uplift. Crustal uplift often coincides with subsidence through a process called isostatic adjustment. This is analogous to the climbing into a boat which sinks lower into the water. Once your weight is added to that of the boat, your net height above the water surface is equal to your height on land minus the amount the boat sinks. Continents similarly sink into the underlying mantle when substantial topographic loads are added to their surface. Lateral escape of crust sometimes accommodates a significant fraction of plate convergence, leaving less available for inducing vertical uplift. Uplift can occur simultaneously or sequentially along many faults that exist in a broad zone of deformation between two converging plates, relating the total horizontal convergence to total shortening, then requires measurements across many faults. An earthquake is a natural phenomena. Like other disasters, earthquakes affect almost every part of the earth and they can be mild or catastrophic. For the past millions of years of geological history, earthquakes, floods and other natural events have helped to shape the surface of our planet. An earthquake may last only a few seconds, but the processes that cause earthquakes have operated within the earth for millions and millions of years. Until very recently, the cause of earthquakes was an unsolved mystery. It was the subject of fanciful folklore and equally fanciful learned speculation by peoples throughout the world. An earthquake is a sudden, rapid shaking of the earth caused by the release of energy stored in rocks. This is a brief definition which students of all ages can master. A full definition of the term, however, would need to include a good deal of more information. Students may be surprised that we speak of rocks and rock layers because in many places the rock material of the earth's crust is covered by accumulations of sand or soil. Remind them that even beneath the sediment in river valleys, plains and beach areas, some kind of rock is always present. Tectonic disturbances in the earth's crust result in the sudden release of energy that creates seismic waves. It may also refer to sudden and violent shaking of the ground, sometimes causing great destruction. They are of three types: shallow, intermediate and deep foci earthquakes. Most parts of the world experience at least occasional shallow earthquakes, those that originate within 60 kilometers of the earth's outer surface. In fact, the great majority of the earthquakes foci are shallow. It should be noted, however, that the geographic distribution of smaller earthquakes is less completely determined than more severe quakes, partly because the availability of relevant data is dependent on the distribution of observations. Of the total energy released in earthquakes, 12% comes from intermediate earthquakes, that is, quakes with a focal depth ranging from about 60 to 300 kilometers. About 3% of the total energy comes from deeper earthquakes. The frequency of occurrence falls off rapidly with increasing focal depth in the intermediate range. Below intermediate depth, the distribution is fairly uniform until the greatest focal depths of about 700 kilometers are approached. The deeper focus earthquakes commonly occur in patterns called Benioff zones. that dip into the earth, indicating the presence of a subducting slab. Dip angles of these slabs average about 45 degrees, with some shallower and others nearly vertical. Beneath zones coincides with tectonically active island arcs such as Japan, Vanuatu, Tonga and the Aleutians, and they are normally but not always associated with deep ocean trenches such as those along the South American Andes. Exceptions to the rule include Romania and the Hindu Kush mountain system in most beneath zones. Intermediate and deep earthquake foci lie in a narrow layer, although recent precise hypocentral locations in Japan and elsewhere show two distinct parallel bands of foci 20 kilometers apart. More than 95% of the world's earthquakes occur in discrete belts throughout the world. The existence of these belts is one piece of evidence in support of plate tectonics. In fact, we know these belts are plate boundaries. Earthquakes occur along all types of plate boundaries, subduction zones, transform faults and spreading centers. However, there are earthquakes which occur within plates. For example, the New Madrid area of Missouri, Charleston, South Carolina and Hawaiian are all places which have a large earthquakes. In fact, in 1811 and 1812, there were 4 very large earthquakes in the New Madrid area, which are believed to have been in the low magnitude 8 range. There are no actual recordings from which to figure out magnitudes. These earthquakes actually rang church bells in Boston over 1700 kilometers away and caused damages as far away as Washington DC, more than 1100 kilometers away. There are also stories that say these earthquakes made the Mississippi River flow backwards for a short time. Earthquakes which occur within plates, that is intraplate earthquakes, are among the remaining mysteries for plate tectonics, because plate tectonics cannot strictly explain their occurrence. In some places such as Hawaii, the earthquakes are related to volcanism, but for the most part intraplate earthquakes are as yet not fully understood. Most earthquakes are at plate boundaries, but there are some intraplate earthquakes. Where do earthquakes occur? In order to explain where earthquakes most commonly occur, one must consider two primary factors. First, external forces must be straining the rock, causing it to move. Second, the rock must respond to these applied forces by suffering brittle fracture, not steady plastic flow. On a large scale, both of these factors can be related to the theory of plate tectonics. Earthquakes occur predominantly at the boundaries of a global patchwork of surface plates, where neighboring plates move past each other. On a finer scale, especially relevant to detailed hazard mitigation efforts, local conditions become important. For instance, earthquakes are most likely to occur along faults, planar surfaces that have already suffered previous earthquake slippage. Within the faults themselves, earthquakes often start at favored locations called asperities, which may be characterized by roughness in the fault surface, a patch of high strength rock or other special properties. As scientists narrow their attention from the perspective of tectonic plates down to the perspective of how the rock within an asperity fractures, our understanding of the earthquake process becomes less and less certain. We can forecast with some confidence the broad regions where earthquakes are likely to occur within the next few decades or centuries. However, our current scientific understanding is inadequate to provide the precise location and timing of the next earthquake to occur. For instance, near San Francisco, at the present time, earthquake risk can be best addressed by society on the broad scale, even as scientists continue to study the details of how, why and when earthquakes occur. In plate tectonics theory, the surface of Earth is divided roughly into 14 major plates, ranging in size from the Arabian Peninsula to the nearly all the Pacific Ocean. The plates are rigid so that motion at the surface occurs primarily along plate boundaries. The plates move across the surface at velocities typically between 10 and 100 millimeters per year. The forces applied to rocks along the plate boundaries build up slowly, and large earthquakes along different portions of a boundary appear to occur independently. In the United States, the Pacific plate borders the North American plate within California, trending north-northwest approximately from the southern Mojave Desert near the Salton Sea to Cape Mendocino near the city of Eureka. Geologists traditionally locate this strike-slip plate boundary along the San Andreas Fault, along which the Pacific plate slides northwards relative to North America. From Cape Mendocino to the Canadian border, the North American plate borders the Juan Dozi Fuca plate, the last remnant of a larger oceanic plate, most of which has subducted into the mantle under the western United States. All along the southern coast of Alaska, the Pacific plate borders the North American plate, again sliding northwards along the Alaska's eastern panhandle. Subduction occurs where the coastline veers west to connect with the Aleutian island chain. One of the largest earthquakes in the 20th century, with magnitude of 9.2, ruptured the central portion of this plate boundary on Good Friday in the year 1964. It devastated the city of Anchorage and generated tsunami water waves that flattened military bases on the coast of Kodayak Island. The plate boundary continues along the volcanic islands of the Aleutians, trending from a pure subduction to a pure strike-slip boundary as it approaches the Russian Kamchatka Peninsula. The central and eastern United States does not contain or border a major plate boundary, and so has many fewer earthquakes. Several US island territories lie along plate boundaries. However, Puerto Rico lies along the boundary of the Northern American plate, and the Caribbean plate. Guam lies along the boundary of the Pacific plate and the Philippine plate. Guam suffered a magnitude of 8.1 earthquake on August 8 in the year 1993. The Hawaiian Islands lie far from any plate boundaries, but are prone to earthquakes associated with volcanism associated with a mantle hotspot. Earthquake hazards in other countries are also concentrated along plate boundaries. The islands of Japan lie along the subduction zones at the eastern edge of the Eurasian plate and have a long history of devastating shocks. The Pacific coast of Mexico, Central America and South America parallels an active subduction zone for thousands of kilometers, leading to substantial risk. From southern Italy eastward through Middle East to Iran stretches a complex pattern of earthquake zones associated with confluence of the African, Eurasian and Arabian plates. Finally, the collision of India riding on the Indo-Australian plate with the Eurasian plate gives rise to frequent earthquakes along the base of the Himalayan mountains. The effects of this continental collision are felt most severely beyond the Himalayas in China, where it causes many of the most damaging earthquakes worldwide in terms of death toll. Earthquakes are common geodynamic processes throughout the world, and has not left Indian subcontinent also. The Indian subcontinent has a history of devastating earthquakes. The major reason for the high frequency and intensity of earthquakes is that the Indian plate is moving in the northeast direction, colliding with the Tibetan plate. This movement of Indian plate is at a rate of approximately 47 millimeter per year. Geographical statistics of India show that almost 50% of the land is vulnerable to earthquakes. A World Bank and United Nations report shows estimates that around 200 million city dwellers in India will be exposed to storms and earthquakes by 2050. The latest version of seismic zoning map of India given in the Earthquake Resistance Design Code of India assigns 4 levels of seismicity for India in terms of zone factors. In other words, the earthquake zoning map of India divides India into 4 seismic zones: Zone 2, Zone 3, Zone 4 and Zone 5, unlike its previous version which consisted of 5 or 6 zones for the country. According to the present zoning map, Zone 5 expects the highest level of seismicity, whereas the Zone 2 is associated with the lowest level of seismicity.